So I will wait for about 1 minute before start. Okay, so let's get started. Okay, so welcome everybody, and now last time we finished discussing a small programming language which is called integer expression, and what we are going to go to today is we will consider a little more sophisticated language called language for predicate logic, and then we will go through some of the process that we did for integer expressions, like we are defining abstract syntax and denotation of semantics, but also there are a few more specific things that's going to happen for predicate logic, which is more thorough analysis of so-called binders and inference rules. So here's a big picture. And just like before, we are studying predicate. So this time we're going to study something called predicate logic. So what is predicate logic? I think if you just imagine Boolean expression in any programming language that you experienced so far, that's pretty close to predicate logic. But there is some big major difference. The major difference is that it's a Boolean expression in any programming language plus quantification. So for instance, some of the predicate logic phrase is gonna look like this. Say for X, for Y. So in our language that we're gonna describe in this lecture for universal quantification and existential quantification range over integers. So for every integer X, for every integer Y, there exists the integer M and integer N such that X times M plus Y times N is equal to 1. And this is actually true. And it's one of the results coming from the number theory. And this is a kind of statement that you can write in predicate logic. And another thing that you can write in predicate logic is something which you think you can immediately see that it's true. For all X, there is Y, such that Y is greater than X. This is another expression that we can write in predicate logic. So in predicate logic, we have just usual expressions that we studied in the first two lectures, the second and third lectures, and also the expressions that you typically write in any programming languages. So it has integer expressions, but it also have universal and existential quantifications. And the reason we study about this predicate logic is because it allowed us to study the key concepts in programming languages in like the one that we already looked at, like abstract syntax, and in a bit more complicated context, also denotation of semantics. But at the same time, it also allows us to study two more things, which are inference rules, which will appear repeatedly in our formalization of many programming languages that you encounter in this course. And also the last bit is that binders. So in predicate logic, we have universal and existential quantification. They are called what I call binders, and they require some careful treatment. So it happens that in old days, people made all sorts of, the various textbooks on logic made all sorts of mistakes on handling universal and existential quantification, especially in relation to the idea of applying substitution. So it allows us to study all these concepts. And there's another motivation. So it allows us to study these 4 key concepts in a much simpler context. And also another motivation is that predicate logic itself is quite important. It plays a role in so-called program logic, which is, you can think of that as some methodology for proving properties of a program, or sometimes you call this axiomatic semantics. And that forms the basis of modern automatic verification tools, and it plays a key role in the study in program logic. So that's why it's worth studying this predicate logic. And so how are we going to study this? So the first things that we're going to look at in predicate logic is, of course, abstract syntax. Abstract syntax of predicate logic. So one thing I forgot to say, that in general, when people study about predicate logic, I mean, their quantifications can range over many different kinds of things. But in our study, we're gonna restrict our focus on particular kind of predicate logic where universal and existential quantification range over only integers. And this kind of predicate logic is sometimes called first order logic. That's because some predicate logic, universal and existential quantification can range over sets of integers, and they are called second order logic. And then this, if the logic that we are considering is a first order logic, it's because it's something that we typically use, and also it allows this, I mean, more sophisticated logic has all sorts of other issues that we don't want to talk about here. So there's what is an abstract syntax of predicate logic? Abstract syntax, just like one before, we're gonna specify abstract syntax by abstract grammar. So what was abstract grammar? It's a grammar which we use to specify a set of finite derivation trees, not how to do the parsing. So it's a grammar which doesn't care anything, doesn't pay any attention on how to do the parsing, instead focus entirely on the specifying the allowed finite trees. So in this abstract grammar for predicate logic, I also said this abstract syntax is an initial algebra, and I'm gonna mention about how we can view the syntax of predicate logic as an initial algebra. It requires some extension to what we already studied with the language of integer expressions. So what's the syntax? The abstract syntax, or the abstract grammar for predicate logic looks like this. It has two non-terminals. One is called integer expression. The other is called assertion. So it's called assert. So integer expression, the grammar for integer expression is exactly the one that we see before. It has a constant. And then it has variables. And then it has the unary operation and binary operations. So there are many binary operations, but in the presentation that I'm gonna give, I'm gonna only consider plus and multiplication. There are other operations like divisions, remainder, and minus, and so on. And the official syntax of integer expression in the textbook includes all of these, but I'm gonna only consider plus and multiplication operation. So it will simplify many discussions we're gonna do. And assertions are essentially it's a language for specifying properties about integer expressions. So the simple property that we can say is a true, which is always true, and also false, which is always false. But then there are some ways to include state properties about integer expression. One property is between two integer expressions, we can compare their equality, we can compare their less, one is greater than the other. And there are many other operations like greater than equal, less than not equal. But we are not, I mean, these are all also included in the textbook, but we are not going to, I mean, include it in when we discuss this predicate logic, the language for predicate logic. So, and then there are other things that we have is the unary operation for assert, which is a negation. And then binary operation, which is a conjunction, disjunction. Disjunctions. And in the lecture, we will consider only the one, the conjunction only. And then there is also the universal and existential quantification. So we have for all, we write it like this, variable and assert. Also, we have exists, variable assert, but I'm not going to, so this one, I'm not going to discuss about this. It's because having the negation, conjunction, and then universal quantification, we can express pretty much all the things we can encode all the things about assertion language, including existential quantification, disjunction, and so on. Now, one kind of warning about this abstract syntax is that, just like I said before, this abstract syntax has infinitely many possibilities. So there are infinitely many constants, infinitely many variables. Also, the operation that I'm talking about, I wrote it this way. There are multiple ways of understanding what's really going on, but some easy way to understand what's going on is there are infinitely many operations, one for each variable. So we have for variable x, we have this operation. Variable y, we have an operation. So on. So this notation describe these infinitely many possibilities. So this abstract grammar is a specification of the language. Abstract syntax, it tells us, okay, what's being specified. So this is specifications, and then that specification should mean something. And then what it means is this abstract syntax. And then I said some easy way to understand abstract syntax is finite derivation trees. Or you can, if you prefer, you can think of this derivation tree as a parse tree according to this grammar. So one example in this case, so for integer expressions, when you write this abstract grammar, really this integer expressions now means the derivation trees that we see before, something like a plus x and 3, or multiplications and minus sign x, then plus of 3 and 4. So all the finite derivation trees form the integer expression, and constant 0, constant 1, and so on, they are denoting finite there's some specific derivation tree, which is a singleton tree. And this minus operation that you see on the top means that it's an operator that takes the derivation tree and put minus sign on the top and so on. Then in this grammar, instead of having just one non-terminal, so we have a two non-terminal, the other one is called assert. And this assert is again finite derivation tree, but subtree can include the finite derivation tree from integer expression. For instance, we may have an equality, and that equality may include two derivation trees. They are coming from integer expressions. Okay. Then also the more complicated one, the more concrete examples can be, we may have some conjunctions, universal quantification over x, and then the quantified formula may be say it's a less than relations for x and y. And then the other conjuncts maybe talk about equality between 3 and then y, yeah, something like y. So this is another instance of finite derivation tree, and there are infinitely many of those. And because things are finite, there are countably many of them. I mean, the tree depth is finite, so there are countably many of them. Okay, so that's a way to understand this. And then from this perspective of this derivation, the finite derivation tree, you can understand this minus in the abstract grammar really denotes an operation that take tree and we put not minus negations as a take a tree and put construct a new tree which put a negation sign on the top, and also this for x, the universal quantification, it takes tree and then it puts universal quantification on the top. So you can view all the cases in the assertions as this kind of operator. And more abstractly, this abstract syntax can be seen as initial algebra. But just like the big difference between the initial algebra that we talked about for integer expression and in this case, is that now we have our signature of this initial algebra. We'll have two types. So I said initial algebra, when I talk about initial algebra, I talk about so-called signature, and which is a bit like Java interface. And then I also talk about algebra, which is a Java class which implements the interface. So Java interface declare types, and Java class provide the implementations. So that's a similar kind of relationship between a signature and algebra. And then I said this initial algebra is in a sense canonical algebra for a signature. And then I said the syntax, abstract syntax mathematically really means abstract grammar means a specification of a signature. Abstract syntax means the initial algebra specified by the signature. Every signature uniquely determines initial algebra up to isomorphism. And that's what we mean by the abstract syntax. And in this case, signature will have two types. One for integer expressions, U, and T for assertion. Because there are two non-terminals, we have one for integer expression and T for the assertions. And then we have a bunch of constants and operations that all comes from this abstract grammar that we talked about. So here's an abstract grammar we talked about here. And these guys are give rise to the constants and operations that should be included in the abstract syntax, in the signature. So if I just give you some examples, there will be equality operation. Then equality operation will take two integer expressions. So its type is it takes two elements of type U and return an assertion, so which is type T. So that's what it should do. And also for all the quantification, like for X, it's a universal quantification take assertion and return an assertion. So it's an operation that take an assertion and return an assertion, and so on. So it's essentially the same as what we did for integer language for integer expressions. The only difference is now we have two types, one type for U and the other type for T. And then now so beforehand when we talk about this initial algebra and signature and so on, we talk about the notion of, okay, before going this, okay, so if you have an initial algebra like this, a signature like this, there are algebra for this. Will provide a set for the first type and implementation for the second type. So it's going to have one set, which is, let's call it as S0. And then S1. Let's use the subscript. Let's use U. So it has a one set for type U, another set for type T, and then it will have an operations like, let's call it equality, which take two elements of type U and return element of type T. And then universal quantifications, which take elements of type T and return elements of type T, ST. And then there is this is one algebra. Another algebra may be something similar. Prime, Cu prime, and return S prime T. And quantifications ST prime to ST prime. So the reason I talk about this is because now in this context, the idea of a homomorphism from A1 to A2 should consist of two functions. So the function h, which maps Su to S prime U, and k, which maps St to S prime T, such that the h and k together preserve all constants and operations. Okay, so the intuition about homomorphism is that it provides a translation from one algebra to another algebra. And now, because there are two types and implementation of two types, U and T, we have to provide translation for implementation of type T, type U. So H is that translation. And we also have to provide translation for implementation of type T. So K is that translation. But they together should preserve the operations defining in the one algebra to the constants and operations defined in both algebras. So what does this mean? And the meaning is actually quite simple. So you say that intuitively what it said, if you look at the meaning of something according to the one algebra and translate it to the other algebra using H and K, that should be identical to interpret, consider the implementation on the other algebra directly. So one example is if we have a checker equality for elements X and Y, and let's use A and B. And then we translate it using K. So A is in S of U, B is in S of U, and this entire thing is in S of T. But if you map whole thing to K, the whole thing is going to be S prime of T. Okay, and that is the same as what we use one. So this one works on S prime of U. Then we translate this A. So this guy is in S prime of U. This guy is also in S prime of U. And this whole thing is in S prime of T. So you can say, so it means equality in one algebra correspond to inter-equality in the other algebra via H and K. So that's what this means. And this should be true for all A and B in S of U. So that's the preservation condition. And then this type of condition should be true for all the constants and then operations there. And initial algebra is the one for that's given a signature. Initial algebra is the one algebra for the signature such that for any algebra there exists a unique homomorphism. Okay? So that's what I mean, the initial algebra perspective, and the abstract syntax that we are defining is really an initial algebra. So that if I just spell out the correspondence, the abstract grammar that I gave you for predicate logic, that's specify the signature. And then abstract syntax for predicate logic. So that's given, that specify the initial algebra for that particular signature. And just like in the lecture before, okay, I said with this initial algebra view, let us have two things. What are the consequences? So the two things, which is first, we can have a syntax-directed definition. So we can define something by case analysis and immediate induction. And induction. And also we can have the structural induction principle in this more complicated language. But as I mentioned, because we have two types, U and T, okay, in this language, if you apply the syntax-directed definition or structural induction, often that involves, in a sense, doing induction on all the elements of type U, which are all the integer expressions, and also doing induction over all the elements of type T, which are assertions. And sometimes we have to, in a sense, move when you consider some sub-phrase, you may, while doing induction on T, you might have to go to the induction on U and so on. So you have to switch from one to the other. The switch happens in this case only from assertion to integer expression, but that's what often happens in this case. Yeah, by the way, if you have any questions in the lecture, anytime you can. So the Robert asked why H is not applied here. And really that the reason is, if you think about what's really happening, so we are really, here we are really want to state equality in one algebra correspond to equality in the other algebra. Okay. A and B are, in a sense, not quite relevant. And we just want to say equality in one algebra correspond to equality in the other algebra. Now, in order to apply the equality on the other algebra, you can't really do it using using A and B. That's because it doesn't even type check. Equality, this equality superscript 1 can only be applied to elements in S prime U. So if you just have an A and B, you have to translate it into the elements, and we can talk about, you can apply this equality in, this equality. Okay. So the line, yeah. Okay, good. See. Okay, so now what we're gonna do? We're gonna use this syntax-directed definition to give a denotational semantics of this language for assertions and integer expressions. So the step 3, denotational semantics. So just like I said before, denotational semantics is a mapping from abstract phrases to the mathematical elements. So you can think of more high level is mapping from syntactic entities to the mathematical entity. Specified in a way, in a syntax-directed way. And I said this is sometimes called compositional way. And then from the practical perspective, the giving denotational semantics is quite simple. You essentially do the case analysis and define something inductively. So for the to give a denotational semantics for the programming language we have to use provide the two functions. The first function is written like this. This is for integer expression. Second function is written like this. This is for assertion. And then the first function, it take integer expression. So it map integer expression to appropriate mathematical entity. The appropriate mathematical entity was exactly the same as what we did for the language of integer expression. It's a mapping from states to integer values. Okay, so where this set of state is really a mapping from variable to values. So state really tells us what are the values of all the variables appearing in the integer expression, and then this once we are given such values, then we can evaluate integer expression and could get a value. So that's what the right-hand side domain is telling us. And left-hand side really means we have a syntactic entity. So we have a syntactic entity get mapped to the evaluator. And then the assertion case, we have an integer expression, no, not integer expression. We have an assertion. And then that assertion get mapped to mapping from states. Now, in this case, if you evaluate an assertion, we get a Boolean value, which is either true or false. So the B is going to be a Boolean true or false. Okay. So, I mean, beforehand, I make this functional aspect more explicit by using lambda notation. So, okay. So this integer expression, I mean, I'm gonna, okay, just first write it down first. So if for integer expression case, is the same as before. Okay, so for instance, integer expressions for variable is lambda, it takes a state sigma, and then it just look up the value of variable x in the state. But so I'm not going to talk much about this, but I will do some simplification in this case. So first, I'm not going to write, I mean, these subscripts, I will omit them often because it will simplify things. Second, instead of writing interpretation in this way to make function more explicit, I will write interpretation in a bit different way, which makes things a bit simpler. So they define the same thing, but this will make it easier to understand in some cases. It really means I have a integer expression x, which take a state sigma, and then now we have to return integer value. The returned integer value is the value of variable x on the sigma. So the integer expression case is the same as what we did before. Now I'm gonna tell you how to do the interpretation for assertions. So because we are using syntax-directed definition, the way to define the semantics of assertion is essentially case analysis. The case we have is true, sigma, false, sigma, and then equality of two expression, sigma. And less than. So we have negation of, I think, P, sigma. And then conjunction and universal quantification. So each of the case, so as I said, syntax direct definition is essentially case analysis. And if we have a complicated case, you can use induction. For instance, the first case, semantics of true on the sigma. Now we have to return Boolean. This always have to be true. Semantics of false on the sigma, it always have to return false. Now the equality, what we do is that we first evaluate expression E1, and then we evaluate expression E2, and check their meaning, whether they are equal or not. So this is a mathematical equality. And this equality appearing here is a syntactic operation. It's an operation that take two trees and put equality sign on top of those two trees, right? So they mean something different. I mean, if you just look at equality everywhere, it looks like, I mean, we say equality means equality. That's not the case. Syntactic, the notation equality, operation equality means mathematical equality. That's what they say. So now I will give you maybe 2 minutes to complete the cases for these are the other 4 cases. 감사합니다. Okay, so for the first case, it's all very easy. So this one is saying you interpret E1 sigma, E2 sigma. So it really means less than symbol means mathematical relationship less than. Negation also the same. It means negation symbol means the negation, no, this negation symbol, this not symbol means that it's a negation for Booleans. Conjunction means conjunction. Sigma. And then the last bit is a bit more complicated. So we have to say, again, universal quantification means a universal quantification, but this one really said for integer n, the following has to be true, which is P has to be true on the sigma, but where we replace the binding for x from any value that already exists to this universally quantified n. Okay. So that's what this last part, which is perhaps a bit, I mean, again, just it's obvious, and it should be obvious because syntax should mean what it's supposed to mean. But the last case requires a little bit of, maybe a little bit unfamiliar to you. Okay. So that's the denotational semantics of this Practicology, and it's defined in the syntax directed way. Now, what can we do with this denotational semantics? And then the next thing we can do with this denotational semantics is to think about the reasoning principle. So this is called inference rules, or justify the reasoning principles. So to talk about inference rules, I first have to tell you about some important concept in predicate logic. We said the P, which is a predicate logic formula, maybe call it assertion. Say the predicate P is true. So P is valid if the P under sigma is equal to true for all sigma. Okay. So this valid means it's true all the time. It's not saying it's true. Sometimes it's saying it's true all the time. So one example of P can be for x exists y, x greater than y. And this has to be, it has to be true all the time, because for integers, not natural number, but for integers, for any integers, you can always find something smaller. So that's a true predicate, true assertion. And now you might ask, okay, is there any way, this valid assertion is quite important. Often the reasoning using logic boils down to reasoning about validity of certain formula. Okay. So like the formula that I showed before, for x, integer y, m, and x times m plus y times n is equal to 1. This is one of the known theorems in number theory. And many results in number theory can be expressed in terms of validity of some assertion. So it's quite important to find some way to prove some assertion is valid, and inference rule provides such a tool. So inference rule notation is written like this. Have a bar, and it's in our particular context, above the bar we have multiple assertions, P1, P2, so on, Pn. Below the bar, we have one assertion, P. And what does this mean is, if P1 is valid, P2 is valid, and so on, and Pn is valid, then P is valid. That's what this rule denotes. And then the purpose of this is called inference rule. And what goes on top of the inference rule is called premise. And then that goes below the bar is called conclusion. And what is the purpose? The reason we are thinking about this inference rule is because we want to have some bunch of inference rules, and then we want to prove validity of assertions just by using inference rule without really going into the semantics. Sometimes going to the semantics is useful, but using inference rule is more systematic and it's more like mechanical. So sometimes you can prove a lot more things using the inference rules. Things more easily using inference rule. Furthermore, inference rules become the basis for automatic way to prove properties to prove theorems in predicate logic. So now, how about the typical inference rule? One example inference rule is, say, if E0 is equal to E1, that implies E1 is equal to E0. So the one you see below, this imply, so this can be understood as E0, E1 negations. So this is what macro expanded version of this implication. And so although I didn't talk about implication, this is something that we can include, and we can provide the meaning of this implication very easily based on what you understand what implication means. And this this is one example inference rule, which is valid. And another inference rule is like this. If P0 is valid, P0 implies P1 is valid and P1 is valid. And sometimes this one is called rule of deduction when you study logic. Okay, now here's an exercise I want you to think about. So I'm gonna write two rules, and then one of them is true, one of the other is not true. Okay, so prove that, pick which one is true, and then also show that that one is indeed true using the semantics, because its validity is well defined. So, and then this rule supposed to mean this relationship. So you can prove that the rule is really is correct, which is officially called sound. Okay, so here's one example. P. And this is first, second one. It looks all similar, but they mean something different. So which one is correct or sound? So I'll give you 1 minute or 2 minutes to think about this. So the correct sound doesn't mean valid. This correct means this guy. So if all the premises are valid, the conclusion is valid. That's what we mean by correct and sound. Validity is a property of an assertion. Soundness, correctness is a property of an inference rule. Okay, so let me tell you the answer. The answer is this number one. It's a sound, but this one is not sound. Okay, why is that? Now, sorry, I think became larger than my quotes. Okay, so why this is the case? So if you look at, the first one, the second one claims that this implication is valid because it doesn't have any premise. So if you look at what soundness means that all the premises are valid, the conclusion should be valid. But there is no premise. So if the second rule said this one is valid, but that's not true. This rule said for any P, if you just, that P implies the same P where any variable can be universally quantified. That's not quite true, right? So this one, say if x is greater than 1, so for x, this is valid. That's not really true. If x is greater than 1, doesn't imply all the numbers are greater than 1. So this one is not a valid state. It is not. The P implies for xp. In general, it's not a valid. And that's why this inference rule is not sound. Second inference rule is, on the other hand, sound. What this means is the soundness in this case means that premise is valid. If P is valid, then for X dot P is valid. So that's what the soundness means. So if you look at this conclusion, which is for XP is not valid, this means for X dot P on the sigma it should be true for sigma in the for states, but denotational semantics of the quantification said this one is true happens when for all natural number, integers, semantics of P on the sigma where X is bound to this natural number. And if this is true all the time, then we say that this universal quantifications has the value true. But the one below, this is always the case. That's because we assume the validity of the assertion P. So validity of assertion guarantees that the one below is always true. So this rule 1 is a sound inference rule. Number 2 is not a sound inference rule. Okay, right. So then the studying about sound inference rule is a huge area in logic. So this is sometimes called proof theory. And we are not really going into the proof theory seriously, and we're gonna just pick some of the rules as necessary. But I just want to mention that the studying about this inference rule is a big area in logic. Okay, so then that brings us to the last part of our study on predicate logic, which is going to be about binders. What's the number? 5 is of binders. So the binder in predicate logic is the one that we are studying is a universal quantification and existential quantification. And intuitively, so what this binder is doing is that it does the three things. It introduces a new variable. So let's just look at universal quantification here. And then you provide a name. To the variable. You just say fix the name of the variable. And then you make the variable available inside its scope. In this case, scope is going to be the body, which is P. Okay, so the body was the name. For the universal quantification, name was X, and then the scope was this body P. Okay, so that's what's really going on. It introduces the variables and assign a name to the variable and make it available within a limited scope. Okay, and that kind of operation happens a lot in many programming languages. So if you declare a local variable maybe in Python, the local variables it creates a new variable, and then it fixes a name. That's what you declared, and it create a scope of the local variable, which is the range on which this local variable is available. But at the end of the scope, the variable just disappears. Now, from this analysis, you can think of this some properties about what these things should do. So morally, if you change this variable x to variable y, and then replace x to y, nothing should really change, okay? Because this name x is not really essential things that's going on. It's some temporary, kind of temporary name that we give to the newly introduced variable. So renaming it shouldn't really make any change at all. The second, so that's the first consequence. Shouldn't make any difference. And then the second consequence is that now if you want to rename or change some variable from, so suppose I have for x, and then inside x x appears in the body of universal quantification. Suppose x appears multiple times. So suppose okay. Suppose that we have a universal quantification like this. Suppose that for the entire thing, I want to apply substitution where I replace x to, say, y plus 2. Okay? So then this substitution shouldn't be applicable here. It shouldn't be applied here. Why is that? That's because this universal quantified variable x, it's a new variable that we introduced by the binder. So on the other hand, the substituting variable x, it's a existing old variable, and which we will call free variable. But so it's a variable outside of this scope. So they are essentially different things. It just happens that they have shared the same name. So this substitution shouldn't apply. And you already know about this, because if you declare global variable x, and then if you locally declare variable x again, the local variable x shadows the global variable, but they are different things. And something like this distinction should happen. So that requires some care in handling this type of binders and variables introduced by the binder. So that's what we're gonna do. So what should we do now? So the first thing we have to think about is the notion of free bound occurrences of a variable, and also the notion of free variable. So I think the best way to understand this, this is very easy concept, but the best way to understand this is to look at some example. Here's some examples. So for every quantification, it introduces its scope. So the first quantifier, universal quantifier, its scope is this entire thing. And then the second quantifier, this universal quantification, the scope is the one that you see there. And then the last for x with its scope is like this. Okay. So each of the quantifier introduce scope, and the variables, you introduced variable by the quantification is only available for that scope. So now let's look at the variable x. So other than this the x appearing in the quantification, we have a first occurrence of x here. This is first. First occurrence here. Then second occurrence here. And the third occurrence. And fourth occurrence. And then for variable y, we have a first occurrence, second occurrence, the third occurrence here. So occurrence means the variables appearing in the expression. It doesn't mean the variable itself. It means its appearance in a assertion. And then for each of the occurrence, we can say it's a bound occurrence or free occurrence. For instance, variable y is called a free occurrence because, I mean, it's not in the scope of any quantified variable for y. Okay? On the other hand, x is a bound occurrence. This number 1 is a bound occurrence because it's in the scope of the universally quantified variable x. So it's bound to the universal quantification here. And then for the second occurrence of y, that's a bound, and then it's bound to the universal quantification here. For x, it's bound, but it's bound to not this universal for y, it's bound to the universal x here, and so on. So we can define for each of the variables occurrence, we can say it's either free occurrence or bound occurrence. And then for variable, given an assertion like p here, given an assertion, we say y is a free variable. We can say y is a free variable p because that's because the y has a free occurrence in assertion p. So if some variable has a free occurrence, we say that's a free variable. So for occurrence, we distinguish free and bound. And for variables, we say some variable is free in a given assertions if it has a free occurrence. Now here's the one exercise I want you to do. So the exercise is that now I want to define an operator, fv, for integer expression and fv for assertion, which take for integer expression case, take an integer expression, and then computes all the free variables that appears in the integer expression. This is what we already did before. For the assertions, we want to define take on assertions and return all the free variables that are appearing in an assertion. So this is what we want to do. And this we already did before. So the exercise I want you to do is to assume existence of this free variable operator for integer expression and define this free variable operator for assertion in a syntax-directed way. So I'll give you 2 minutes to do so. Okay, so the definition is pretty simple. So, but there are some cases where you have to be a bit more careful. For true and so free variable of false, it's an empty set, and free variable of E1. So we do case analysis. I think maybe greater than is what I use. Greater than, in this case, it's a free variable of E1 union free variable of E2. So this is for integer expressions, which we already defined. And then for free variable of negation of P is free variable of P, and free variable P1 and P2. This is a free variable of P1 union. Compute the set of free variable for P2. So far this is very simple, and just do the kind of call for subphrase and take the union. And the only a bit tricky part, which is not also very hard, is this universal quantification. In this case, what you have to do is you compute the free variable P, and then you remove X because X is bound, and that's what you have to do. So that's the idea of free variables, free bound occurrence, and the notion of free variable. And this is the operator that you can use to compute this. Okay, and remaining 5 minutes, the one I want to talk about, the last bit of today's lecture, is substitution. So substitution, if I remind you of what it is, it's a mapping. So substitution is a mapping from variable to integer expressions. And then we use notations like x to, say, x plus y to mean a substitution which replace, maybe also another one, y to z, to mean a substitution which replace x by x plus y by z, and then all the other variable it doesn't touch, it doesn't do anything about this. Okay, and then the last bits of this substitution is applying these operators of applying substitution expression. So this is an application of delta substitution delta to expression E. So for example, if you have some x plus y, but then we substitute by x becomes x plus y, y becomes z, then the outcome is going to be x plus y plus z. So now here's another exercise I want you to do. So the exercise is, now we define the substitution for the substitution operator for integer expressions, but now define substitution operator for assertions in a syntax-directed way. This is more tricky, and this is the part that many logicians in the past make a mistake before. Syntax-directed way. So I'll give you 2 minutes to think about this, and then I will give you an answer, and then I will go through the answer again in the beginning of next week. So we can finish off this part next week. So I will share this handwritten notes. Okay. My handwritten notes are on the course webpage, and then so then what I'm writing, I will try to make it also available either in KLMS or in the GitHub. So while you're solving this, let me mention two potential problem. With the first potential problem is, if you define in the wrong way, then suppose I apply the substitution like this, then the wrong definition may lead to something like this. So another potential problem. So this is quantifications should block substitution, but you are not really blocking this. The second problem is, so if you do the substitution in the case, you might end up with, this is another wrong instance. That's because x here, this x in the bound x, they are different. The x on the substitution means free variable, the universally quantified x is a bound variable, but it happens that the x after substitution means the same thing. And this is another problem. This is also well known. It's called variable capturing problem. So I will go through the answer for this next time, but I think I want to give an answer for only one case. So it's really syntax directed definition. So almost all the cases are very easy except the quantification part. So this is a difficult part, and the definition looks like this. P. Something that doesn't appear. So give me 1 more minute, then I'll finish maybe in Y. So what does this tell us? This tells us that when you apply the substitution delta from outside of the quantification to the inside of the quantification, you have to change delta. So that's what it tells us. How should it change? It change so that delta now map x to x new. Okay, so anything that delta know about x is all forgotten. So then now this new delta will map x to x new. Then x new is a variable that doesn't appear that satisfy the condition that's written here. It say that for variable y appearing in P except x, so for any variable y appearing in P except x, we consider what we would get after applying the substitutions on this variable y. So that's what this delta of y tells us, and collect all the free variable there, and y new shouldn't be any of those free variables. So this update part take care of the problem A. So this updates. So update take care of problem A, and then this choice that's written here, it take care of problem B. Second problem, that's because y new is chosen such a way that the type kind of problem in B will never appear. So I'm going to talk about this more on the beginning of the next Monday. Okay, so that's it for today. I'm going to wait for about 5 more minutes. So if you have any questions, you can ask me. Okay, thanks all for coming.